All right, let's get right into it. When you're engineering a drone, picking the battery, well, it's not just another item on a checklist. It is the mission-defining decision. It dictates absolutely everything from how long you can fly to how much you can carry. So yeah, let's dive into this critical component. You know, the choice between lithium polymer and lithium ion, it goes way beyond just chemistry. It's the fundamental engineering trade-off that sits right at the heart of your drone's entire reason for being. So what are you building, a sprinter or a marathon runner? Honestly, that one question is going to guide our entire discussion today. So here's our game plan. First, we'll talk about why this choice is so incredibly critical. Then, we're going to learn to speak the language of batteries by decoding what's on the label. After that, it's the main event. We'll pit the two chemistries head-to-head, see how they actually perform under stress, and finally, figure out how to match the perfect battery to the right mission. Let me be perfectly clear. If you mismatch your battery and your mission, you're setting yourself up for failure. We're talking about everything from a long-range mapping drone getting a premature low battery warning when it's miles away, to a heavy lift rig just losing power and dropping out of the sky during a critical lift. The battery truly is the heart of the system. If it gives out, the mission is over. Simple as that. Okay, so before we can even begin to compare LiPo and Lion in a meaningful way, we have to get on the same page. We need to understand the universal language that's printed on every single drone battery out there. This is where all the core specs live, and for any serious engineer, understanding them is completely non-negotiable. First thing you'll see is the S rating. This is super straightforward. It just tells you how many 3.7 volt cells are wired up in series. So a 4S battery, that's 4 cells for a nominal voltage of 14.8 volts. A 6S pack, that's 22.2 volts. And here's why that matters. Higher voltage means more efficient power delivery. For the exact same power output, a higher voltage system draws less current. Less current means less heat and way less stress on all your components. Now, the S for series often comes with a partner, the P for parallel. It's pretty simple. Series adds voltage, parallel adds capacity and current handling capability. So if you see something like an 8S4P pack, what does that mean? It means you have 8 cells in series to get that high voltage, and then you have 4 of those series strings all connected in parallel to multiply the total capacity and the amount of current the pack can deliver. Next up is the C rating, or the discharge rate. Think of this as a multiplier of the battery's capacity. For example, if you've got a 2,000 milliamp hour battery with a 10C rating, you just multiply those together, it can theoretically, and I stress theoretically, discharge 20 amps of current. This number is absolutely vital for performance drones because LiPo batteries, just because of their chemistry, have way higher C ratings than Lion cells. This is their secret sauce for delivering those massive instant bursts of power. But, and this is a big but, a word of caution. The C rating has become a notorious marketing gimmick. As this quote puts it so perfectly, a lot of manufacturers are just blowing unicorn smoke. When you see a label claiming a 100C rating, you should be very, very skeptical. It's often physically impossible. That's why understanding the real-world test data, which we're about to get into, is so much more important than just trusting the number on the sticker. Okay, now that we're all speaking the same language, it's time for the main event. We are putting the two titans of lithium battery chemistry head-to-head. Let's really dig in and see where each one shines and where each one, well, falls a little short when it comes to powering our drones. The absolute best way to think about this is this sprinter versus marathon runner analogy. It's perfect. LiPo batteries, with their soft, flexible pouch construction, they're the sprinters. They are built for one thing, explosive, high-power delivery, right now. On the other hand, Lion batteries, which you usually find in those rigid metal cans like the 1865s, they are the marathon runners. They are all about endurance, about packing in the maximum amount of energy for the long, long haul. And what's so cool here is how the numbers totally back up our analogy. Just look at energy density. That's how much energy you can cram into a kilogram. Lion is the undisputed champion, with some cells hitting an incredible 450 watt-hours per kilogram. That's what gets you those crazy long flight times. But then you look at power density, and LiPo is just in another league entirely. Lion also takes the win on cycle life, often lasting twice as long, and that hard metal can, well, it's obviously a lot tougher than a soft pouch. So these differences in chemistry aren't just numbers on a chart. No way. They have a direct, and I mean measurable, impact on how your drone actually flies, especially when you push it hard. So let's talk about a really critical concept called voltage sag. Think about it. When you punch the throttle, you're asking for a massive amount of current. That current has to flow through the battery's own internal resistance, and that causes the voltage to drop. It's just basic physics. A battery with higher internal resistance, and that tends to be Li-ion cells, is going to have a much more severe voltage sag. This is a big problem because it can actually trick your flight controller into thinking the battery is dead way before it's truly empty. And this graph shows it perfectly. This is a discharge curve for a Li-ion cell at different current draws. See the 1C curve? It's a nice, gentle, predictable slope. But now, look at the 8C and 10C curves. Whoa, the voltage just drops off a cliff right at the beginning. That massive, steep drop, that's voltage sag, right there, visualized. You can see it happening. Now let's look at some real, hard data. In this test, we've got 3 LiPo packs, all with different capacities. The trade-offs are crystal clear. The big 5,000 milliamp hour pack gives you double the flight time of the smallest one, and its voltage sag is half as bad. Sounds great, right? But it also adds almost 200 grams of weight. That is a huge penalty. So the takeaway here is that even within the same chemistry, it's always this delicate balancing act between capacity, weight, and performance. And that brings us to our final and frankly, most important section. We've gone through the theory, we've looked at the data, so now let's make it practical. How do you actually choose the right chemistry for your specific mission? You know, it really just boils down to this. For any mission where endurance is king, we're talking long-range surveillance, agricultural spraying, stuff where you need to be in the air for an hour or more. Li-ion's incredible energy density makes it the only real choice. But for any mission that demands raw power and agility, like FPV racing or heavy lift cinematography, LiPo's ability to dump massive amounts of current is something you absolutely cannot live without. So after all that, we come right back to where we started. It's all about that core trade-off. Power density versus energy density. Sprinter versus marathon runner. The choice between LiPo and Li-ion is a strategic one, and it forces you to decide what's more important, instant power or long-term endurance. There is no single best battery. There's only the best battery for your mission. Hey, if you found this technical deep dive valuable and you want to see more content just like this on drone engineering, flight dynamics, component analysis, please consider supporting our work. The best way to do that is by joining the Quad Drone Lab channel membership over on YouTube. Your support is what allows us to keep doing this kind of independent research. And I'll leave you with this final thought to chew on. As Li-ion tech gets better at delivering power and LiPo gets better at storing energy, those lines are starting to blur. So is the future some kind of hybrid system that gives us the best of both worlds? Or are we on the verge of a solid-state battery revolution that's going to make this entire debate totally obsolete? Something to think about.